Hey everyone, and welcome. Today, we're diving into calculus, but forget about just memorizing a bunch of rules. We're going to build a powerful problem-solving toolkit, and we're going to use it to crack some really complex problems. Let's jump right in.
Okay, so take a look at this. I mean, where would you even begin with this thing, right? It looks absolutely terrifying. This is going to be our main challenge today, and believe it or not, our mission is to figure out how to solve it without even breaking a sweat.
You know, to solve any puzzle, what do you need? You need the right tools. And that's exactly what we're going to do here. We're going to build our calculus toolkit piece by piece, and then we're going to use it to crack this code wide open.
All right, let's get into it. Section 1, the foundational toolkit. Every good mechanic starts with the basics, right? The essentials you're going to use over and over again.
So let's start with our trusty hammers and screwdrivers. You've got the power rule for x to the n. Think of that as your adjustable wrench. It works for any variable raised to a power. Then there's e to the x. Its derivative is just e to the x. It's kind of like a self-replicating screw, which is pretty cool. And of course, sine becomes cosine, which acts like a waveform calibrator. These are the absolute basics, the foundation we're going to build everything else on.
Okay, basics are in the belt. Now it's time to level up. Let's talk about some calculus combo moves for when things start getting a little more tangled up.
First up, the product rule. So what happens when you've got two functions multiplied together? It's actually a pretty straightforward little recipe. You take the first function times the derivative of the second, and then you add the second function times the derivative of the first. That's it. It's a really clean, super reliable technique.
And now, for the big one, the chain rule. I know this can seem a little tricky at first, but honestly, the best way to think about it is like peeling an onion. You've got these functions nested inside each other, right? The rule is simple. You deal with the outer layer first, then you move to the layer inside that, multiplying as you go. It's all about working from the outside in.
Let's give it a try with this one. The derivative of sine of cosine of x. Okay, so what's the outermost layer of our onion here? It's the sine function. So we're going to deal with that first and just pretend for a second we don't even care what's inside.
We know the derivative of sine is cosine. Simple enough. So we just apply that to our outer layer and we get cosine of, well, whatever was inside. In this case, that's cosine of x. See how we left the inside part completely untouched for now?
All right, for the final step, we just have to multiply by the derivative of that inner layer. And the derivative of cosine of x is negative sine of x. So we chain them together, and our final answer is cosine of x, all of that times negative sine of x. See? We just peeled the onion.
Okay, our toolkit is officially stocked up. I think we're ready. It's time to go back to that monster problem from the beginning and put these new tools to the test.
Remember this beast? Yeah, it probably looks just as scary as it did before. And you might be thinking, okay, I'm going to have to use the quotient rule and the chain rule, and oh man, it's going to be a huge mess. But what if I told you there's a much, much better way?
Here's the secret. The single most powerful tool in our entire toolkit for this specific problem, well, it isn't actually a calculus rule at all. It's simplification. Seriously, the best problem solvers, whether it's in math or, well, anything, they always look to simplify the situation before bringing out the heavy machinery. It's all about clearing the clutter so you can see what you're really dealing with.
So let's look closer at this thing. Does that pattern tan of a plus tan of b over 1 minus tan a tan b, does that ring a bell? It should, right from trigonometry. That's the angle addition formula for tangent. It's just tan of a plus b. In our problem, a is 2x and b is x. So that whole complicated mess of a fraction just collapses. It becomes tan of 2x plus x, which is just tan of 3x. How amazing is that? And just like that, the impossible becomes, well, pretty trivial. What's the derivative of tan of 3x? That's a simple chain rule problem now. It's secant squared of 3x, and then you multiply by the derivative of the inside, which is just 3, and solved. The code is cracked.
You know, this just goes to show, sometimes the hardest part of a problem isn't the complex calculation. It's having the wisdom to step back and look for the simple path forward. But okay, what happens when you can't simplify? What about problems that are just genuinely tricky from the get-go? For those, we need to pull out some specialized, professional-grade tools from the bottom of our toolkit. So with the tools we have now, we can totally handle a variable raised to a constant, right? Like x squared. That's the power rule. And we can also handle a constant raised to a variable, like 2 to the power of x. We have a rule for that too. But what about this? A variable raised to the power of a variable, x to the power of x. None of our basic rules are going to work here. This is a special lock, and it requires a special key. And that special tool is called logarithmic differentiation. It is designed for exactly this kind of problem. And its secret power comes from a really unique property of logarithms. They let you grab an exponent and just bring it down in front as a simple multiplier. It's a total game changer. So let's just quickly walk through how it works. First, we'll set our function equal to y. Now, step 2 is the magic move. We take the natural log of both sides. Why? Because it lets us use that awesome log property to bring that pesky exponent x down in front, turning it into a multiplier. Now look at what we've got in step 3. On the right side, it's just x times the natural log of x. Hey, that's a job for the product rule. We know how to do that. From there, we just differentiate, do a little bit of algebra to get the derivative by itself, and we're done. It's this brilliant process that turns a problem that looked impossible into one we can solve with the tools we already have. So, what's the big takeaway here? Calculus isn't just some dusty list of formulas to memorize. It's a dynamic, powerful toolkit that you build over time. The real skill is learning which tool to pull out and when to use it. And it kind of makes you wonder, right? What other impossible problems out there are really just waiting for someone to apply the right tool?